welcome to Securing Open Source Software, end-to-end at massive scale together. My name is Jennifer Furnick, and I'm joined by my colleague, Christopher Robinson. In this presentation, we'll be speaking about securing the open source ecosystem. So to begin, we'll share a little bit about ourselves, myself from the perspective of a security researcher and as someone who in a past life designed and ran cryptographic systems that protect tens of billions of dollars in daily transactions, and Crobe from the perspective of someone who helped coordinate some of the most impactful vulnerability disclosures in our industry over the last 7 to 8 years. We'll also share lessons learned from these experiences in coordinating vulnerability disclosure. We'll talk about why securing the open source ecosystem matters. We'll share several challenges to securing open source software at scale, and we'll offer a threat model of the open source ecosystem because securing open source software is way more than preventing malicious commits. We'll also talk about why we believe that the insecurity of the open source ecosystem is accelerating based on things like the speed at which new vulnerabilities are exploited in the wild, the increased use of supply chain attacks, and advances in computer science that make exploitation faster and easier than ever. Finally, we'll discuss techniques for reducing vulnerabilities at scale, the status quo for coordinated work to improve the security of the open source ecosystem, and share how the Open Source Security Foundation is scaling the efforts of security researchers, as well as share a bit about some of the resources and opportunities to get involved with us. So my name is Jennifer Furnick. As mentioned, I'm the Global Head of Research at the security research and consulting firm NCC Group. I'm also one of the co-founding board and technical advisory committee members of the Open Source Security Foundation. In a past life, I was a cryptographer and a quantum computer scientist, and previously was the security architect and later led a large security team at a global bank. And my background academically is in quantum computing, systems engineering, and artificial intelligence.
Thanks, Jennifer. I'm Crobe. I've had the great privilege to work within open source and security for a great many years. I've had the honor of working on a lot of high-profile, critical coordinations within the community and within the larger technology industry. I've worked with Red Hat Product Security for 6 years before I came here to the Intel Corporation. I currently am the working group leader for the Vulnerability Disclosure Working Group and the Developer Best Practices Working Group, part of OpenSSF. And I've done some stuff. I've seen some things. Crazy. And we're going to share some of that insight today. The OpenSSF is an assembly of very prestigious and very humble folks, great and small, organizations big and small. We've all come together focused on the mission of securing open source software for the larger community benefit. We're going to start off today where I'd like you to imagine a world. Imagine a world where there's a security researcher. They find what they feel is a critical bug in an open source cryptographic library, and they want to see it get fixed. They feel greatly that they need to participate in a process called coordinated vulnerability disclosure. So they search around the internet looking to try to find the developer or the maintainer, and it's not very easy. There's no website, there's not any centralized place where this development team hangs out. Eventually the researcher finds out that there's a GitHub repo that unfortunately hasn't been updated in about 3 years. Not deterred, they continue searching, and they find on a mailing list, that another project is using that same cryptographic library's name in some of their posts. So they reach out to those developers, and they find out, yes, indeed, this team forked that original project. They found a lot of good value in it. Unfortunately, these folks, they aren't security people. They know some people that do security, but they're not security people themselves. So they ask, can we include some extra people? They reach out an IRC in their mailing list to try to find additional people to kind of help out, figure out this problem. Now, on that mailing list happens to be a group called Megacorporation. Megacorporation sells a commercial security package that uses this library, and they're very excited that the reporter found this issue, and they want to work with them on vetting out the proof of concept, kind of triaging what the impact is. They will issue a CVE for this. It's going to be great. So they say, give us a little bit of time, we'll get back to you. The researcher waits and waits and waits, and they reach back out And eventually Megacorp says, yeah, this is an issue. We acknowledge it's pretty bad, but unfortunately we have a new product release coming up within the next 6 months, so we can't issue the release today. Can we wait until that product's release, kind of coordinated around then? Researcher isn't super happy about that, but they agree. And then Megacorp also mentions that there are several other major vendors they're aware of that use this library that they want to include in kind of the eventual remediation. At the same time, around this time, that fork developer, that original development team, they had some free time and a lot of coffee, and they said, hey, we figured out the fix. We posted it upstream. Everything's great. Kind of not ruining, but kind of stepping over the kind of agreed upon disclosure timeline. And this is where things start to spiral out of control. The internet starts reporting that there were exploits of several major vendors that use this. A couple of them actually seemed to pick it up in a major container platform, and that image was downloaded, thousands of times in the last month. And a domestic telecommunications company picked that up, and now they are being reported as vulnerable. A huge internet magazine puts out a headline: "Cracked crypto creatively crumbled by boffins for mega headaches. The internet's on fire." It seems to have gotten pretty bad pretty quick. Or another scenario is that researcher never was able to find anyone to report that flaw to. They try, they eventually post their exploit into their Git repository, they write a blog about it, and they get a prime talking spot at a major security conference. Let's call it Hat Black, for example, because at the end of the day, no one was able to help them. And that's where we're here to talk about today. While this is all kind of based in a thought experiment, a lot of this stuff happens more frequently than you think. Back in 2018, there was a developer of an open source library, and essentially, they didn't see a lot of value in continuing to maintain it. And some random stranger on the internet said, hey, I'd like to help out. I'll pick up maintaining this. And the developer said, you know what? This guy mailed me. I don't get anything for maintaining this module, and I don't even use it anymore. Haven't for years. So he let this complete stranger start to maintain it. And at first, everything seemed fine, but over a series of commits, this new maintainer was found out that they were secretly baking in a backdoor to do Bitcoin mining as for users of this module. So this incidents, these types of things can happen a lot more than you think. Let's reflect back to the granddaddy of them all, Heartbleed. It was a very popular open source library, and still to this day is. And it's basically, it helps with cryptography on the internet. And at the time, this researcher found this problem, and there were something like 500,000 servers on the internet that were potentially vulnerable. So the public disclosure happened on April 7th, 2014. And just a couple months later, in June, there were still 309,000 of these devices that were potentially vulnerable. Flash forward 3 years after that, that number dropped to 144,000. And even just a few years ago, in July of 2019, over 91,000 devices were still vulnerable to this very public, very severe problem. And kind of thinking about the issue, at the time, about 500,000 of these secure servers that ran internet banking, online commerce, were potentially vulnerable to having their servers' private keys or session cookies or passwords taken. And to think about it, the root cause of the issue was you had two incredibly skilled open source developers that worked kind of full time on this project, and that was it. And you had thousands upon thousands of downstream consumers that were leveraging this work, but you had two folks that were basically responsible to develop, maintain, test, and review about 500,000 lines of code. More work than is feasible for a team of two that really they weren't paid to do it. And that is the kind of the crux of a lot of our problems here. The security of open source, our theory here is the security of open source is the security of everything. A lot of research has happened over the last several years to show that free and open source software has a substantial impact on the global technology landscape. Anywhere between 80 and 90% of modern software uses open source. Looking at those things, a report recently found that about 84% of these code bases had at least one vulnerability, with the average being about 158, depending on those larger code bases. And thinking about it, the average age of some of these libraries in between when they had updates was over 2.5 years. Looking at the CVE population over a period of 10 years, it quadrupled in volume in just 10 years. That's the amount of issues that were found and hopefully fixed in that time frame. And looking at, when you think about the problem with open source, a lot of times you have an issue with indirect dependencies. And when you report an issue to the project, sometimes these issues can go for over 218 weeks, one study found. And once it's reported to that development team, it can take 4 weeks to resolve, if it's ever resolved. A lot of stuff going on there.
So, what are the challenges of securing open source software at scale? What makes open source development models so impactful is also what makes them so difficult to secure. So we can think about, the various things where open source differs from other types of software development models. So to begin, we have this deobfuscated public-facing source code, which is reducing the barrier to entry in that attackers need not reverse engineer the binaries. There's also this distributed community-driven development model where contributions can come from many sources and at times even from unknown third parties. At times as well, I think that security and privacy folks are sometimes we give into this tragedy of the commons where we have thought that just because someone has looked at the code that they necessarily have looked at the code, but in practice this may very well not be the case. So we start to see this lack of consistently deployed security standards, reviews, and tooling across open source, resulting in weaknesses at various points in the secure software development lifecycle, even where easy wins for security could have actually happened. So this is somewhat related to this idea that people may not have always looked at the code. And we extend upon this by thinking about the fact that in many cases, open source projects have a decreased capacity for vulnerability remediation, so writing the patches, and even worse for incident response, particularly for smaller projects and those without a mature security program. But as we've seen historically and up to the present day, even this is true for many of the larger projects as well. On top of this, and we'll talk about this a bit more later, there are entirely different economic incentives for open source developers and maintainers compared to enterprise developers and maintainers, compared to the attackers, both security researchers and threat actors. So we have all of these different competing factors that are bringing together this challenge in securing open source. And in spite of all of this, we have these incredibly high value targets that are foundational to many of the technologies that power our world and the internet itself. So let's think a little bit about threat modeling. Open source security is about way more than just vulnerabilities in source code, and there's also a breadth of ways we can think about how these vulnerabilities could get introduced. So we have this broad attack surface that begins before any code is written. It extends to every individual developer's local machine and network, and all of the way through this broader project infrastructure out to even the package management ecosystem and beyond. So in the ideation phase or the concept phase, we have to think about the risks of the entire tech stack. We also have to focus especially on areas of enhanced risk, like cryptography and secrets management, operating system kernels, anything around container orchestration. When we think about the actual development environment, we have to think about the maintainer's machine and interest that an attacker may have in making malicious commits to a repo or to preview forthcoming changes or otherwise exfiltrate sensitive information. So we've seen, for example, malware which sought to exfiltrate a developer's NPM access tokens, or the Xcode Ghost supply chain attack dating back to 2015, in which malicious versions of Apple's Xcode development environment were distributed. So we can move beyond not just thinking about the developer's local environment, which could be compromised in many ways beyond the couple of examples that I've given, but let's extend this to think about the infrastructure or the project itself. So there can just be mistakes in code that a developer didn't mean to introduce but happened to be there. This could be resulting from copy pasting insecure code from Stack Overflow, or just in general using insecure software development practices just by mistake. It could involve committing secrets or to source code or to packages. And it could also involve leaving debug functionality open such that it can be abused as a backdoor by a threat actor. We can also think about external contributions, so contributors who may introduce malicious code either independently themselves or through the compromise of a legitimate developer's contributions. So this can have to do with identity and access management of developers. It can relate to insecure CI/CD pipelines and in which a range of attacks can occur. It can be compromises to build systems, even though there's been some great work over the last several years around build pipelines and verification, especially things like reproducible builds and binary transparency, which can solve some but certainly not all of the problems here. These problems are amplified by a lack of pipeline security tooling, static analysis, fuzzing, as well as in instances where there's a lack of platform security or operating system level protections or runtime protections. It's really this defense in depth together that can help make things more secure. If we go beyond this, there's also the package ecosystem itself. So individuals may typo squat to insert malicious packages. There may be a direct compromise of legitimate packages, and they may also introduce things like malicious dependencies. There's much more beyond this, but even if we want to think about these particular problems and extend it to vulnerability disclosure, there can be inaccurate security contact information. A project may go unmaintained. The maintainer may not see the bug as a vulnerability to security or be unable to write the patch. There also may be insecure communications methods, including projects that would like you to report security vulnerabilities as public issues, and patching in public may allow for the reverse engineering in advance of forthcoming patches to infer not yet public vulnerabilities. So there's much more we could talk about, but probably in the interest of time today, I would direct the interested listener to the Threats, Risk, and Mitigations in the Open Source Ecosystem paper published by Michael Scovetta of Microsoft and several collaborators from OpenSSF. So let's talk about vulnerabilities in the open source ecosystem. Ultimately, open source security keeps getting worse. On average, it's taking years to detect a typical vulnerability in open source software. For example, data from GitHub last year said that the average vulnerability on GitHub goes undetected for 4 years, and even critical vulnerabilities take more than 2.5 years to get disclosed. What's more, exploitation of vulnerabilities in the wild is happening faster than ever before. This is true for both open source and proprietary software. A number of reports have stated that the number of days has dropped from weeks down to just on average about 3 days between a vulnerability being publicly disclosed and exploitation being observed in the wild. And this has happened over just the last few years. And this is true for both proprietary and open source software. Ultimately, threat actors don't really care what licenses our software uses. However, reporting from Rand Corporation has even further demonstrated this point by stating that it was found that exploitation of vulnerabilities of open source in the wild do not actually die off faster than those for proprietary software. Now, why is this happening? Part of it is developers seem not to be getting any better at writing secure code. GitHub used their tool CodeQL to study several thousand popular GitHub libraries and the rate of vulnerabilities being introduced to them between the years of 2016 and 2020. Ultimately, the results were not very promising. And I quote, "A line of code written in 2020 is just as likely to introduce a security vulnerability as a line of code written in 2016." So things are not getting better. And on top of this, applications are growing in complexity. So software complexity can derive in part from both direct and transitive dependencies, which compounds the risks of these dependencies the more and more dependencies there are in the dependency chain. So let's go a little deeper about what that means. Okay, so transitive dependency risk. Even if your code is in the rare instance free of vulnerabilities, your code itself probably depends on something which itself is full of vulns. So we can imagine it, vulns on vulns on vulns, all the way down. And what is the data that really backs this up? We know from recent reports that open source projects have an average of 180 package dependencies. Some of them have even up to 1,000. We also know that the 50 open source projects with the most projects depending upon them had an average of 3.6 million downstream dependents. We further know, to really amplify why this matters, that vulnerabilities in open source software have been central to major breaches. So if we think about the Equifax breach of 2017, it was based upon a vulnerability in Apache Struts, an open source framework. And we also know that they are often not found until decades after their creation at times. So every year we write more and more lines of source code than ever before. In 2020, 60 million new repositories were created on GitHub with around 1.9 billion contributions. We also know that vulnerabilities seem to scale proportionately with lines of code. Even if you don't want to measure the size of software or the complexity of software based on lines of code, you'll see similar patterns around this scaling of the introduction of vulnerabilities. We also see that the number of reported vulnerabilities in open source code bases is growing each year. And furthermore, we have reasons to believe that the number of vulns being reported is radically lower than the total actual number of exploitable vulnerabilities in the wild. So we might ask ourselves, if we stay on our current trajectory, will the security of open source software get better or worse? And without serious and coordinated intervention, I think it will get worse. The number of vulnerabilities in the wild outpaces the speed at which the security community can patch or even identify those vulnerabilities. And each day, the world gets more lines of source code than it ever has before. As a consequence, the generally inadvertent creation of potentially exploitable vulnerabilities increasingly outpaces the rate at which we can search for and remediate them, and this problem is only getting worse with time. So ultimately, we have this problem that security as it is practiced now does not scale at the rate needed to keep up with things, to make them at least as secure just as they were yesterday. And what's worse than that is that we have compelling reasons to expect this to get even worse for defenders. So in this slide, I'm going to introduce 2 points. The first of these points is that the economics of exploitation for threat actors offer them a considerable advantage compared to the economics of patching for defenders. And this is especially true for open source software. So threat actors don't generally have to care about things like policy or law or CFAA. Unlike patching, exploiting open source software vulns does not actually require multi-stakeholder coordination. On top of that, if we think just about incentives, threat actors are incentivized to successfully exploit vulnerabilities, but in contrast, security researchers are not generally incentivized to write patches, and neither are open source maintainers. So threat actors' number one priority is to exploit vulns, but in contrast, open source maintainers' number one priority is the core functionality of their project, not writing or applying patches, or making sure that they're ready for enterprise consumers or people that are working with different threat models. In addition to this, the economics of open source compared to closed source software differ. While with enterprise kind of proprietary software, we have certain expectations of software maintenance and security, open source is at your own risk, with the understanding that the developers of these code bases may not have the same goals, threat model, or priorities that you do. As a result of all of these interrelated factors, we see a decreasing length of time between vulnerability discovery and exploitation, as well as between vulnerability patching and exploitation. So the second point that I want to make is that we have yet to see the true potential of techniques for finding vulnerabilities at scale. What's simultaneously exciting and terrifying to me is that the technologies that can be used to hunt vulnerabilities at scale are dual use in nature. They can be used by the defenders or they can be used by our adversaries. And as the cliche goes within our field, it is our adversaries only have to get it right once. So the uncomfortable truth is that scalable vuln finding helps our adversaries too. So what are the different ways that we can think about these scalable bug hunting methods? These certainly include, large-scale fuzzing projects, vulnerability discovery query languages like CodeQL, various flavors of innovations in program analysis, sometimes applications of machine learning to identifying particular examples of bug classes, and all methods by which attackers will be able to scale their findings as quickly as we will. I think that this is compounded, however, by recent work over the last 5 to 8 years, I would say, in automated exploit generation, where we're seeing that even for small, poorly incentivized academic studies, that there has been considerable progress in automating the chaining of exploits or the chaining of an ultimate attack. So, even if you don't buy into the idea that computer science will eventually have a sufficiently advanced, scalable, automated exploit generation in the near term, even with the most restrained version of our hypothesis, namely that there are at least some level of efficiency gains possible for vulnerability exploitation, this is nevertheless concerning. Furthermore, we have reasons to believe that large language models like GPT-3, which have shown themselves to be very good at learning not just from a corpus of internet text, that they've been able to be generative. So even when asking these models to generate novel things, be they images or stories with particular natural language descriptors, we've seen that they're capable of generating novel code as well. So how do we reduce vulnerabilities at scale? To solve this problem, I think we need to just not have security research, but security research at internet scale. Traditional vulnerability research and the ongoing whack-a-mole to find CVEs can only take us so far, and ultimately it makes its highest impact when we prioritize for the criticality of the target system, either because it is inherently foundational to the internet or to enterprise software, or because it is an upstream dependency to those core pieces of infrastructure, or because it presents subtleties of implementation that make it particularly hard to secure. So we might see this in cryptographic libraries or things with like low-level machine code. Else, maybe because it puts a targeted population, ecosystem, or other single point of failure in the internet infrastructure at risk. So this is thus the motivation for this entire talk, particularly here at Black Hat among security researchers of a broad and range set of technical subspecialties, and particularly within the community track, because we believe that it is only through coordinated and strategic effort that security researchers can attempt to outpace the in-the-wild exploitation of vulnerabilities in open source. So how do we reduce vulnerabilities at scale?
Right, Jennifer. Now, so our challenge is, how do we reduce these vulnerabilities at scale? That there are a traditional kind of cybersecurity framework, prevent, find, and detect is a way to handle this. But we need to figure out ways to eliminate whole classes of bugs. Doing individual vulnerability whack-a-mole, onesie, twosie, one at a time, does not work, will not get us to the space we need to be in. We need to be able to eliminate whole classes of problems like SQL injection or cross-site scripting or remote code execution. Be able to eliminate these things, whole swaths of hundreds of vulnerabilities at once. We need to understand and take a look at the threat model of open source. Most modern software today isn't a monolithic code base. It's a composed app where you're borrowing little bits and pieces of software here and there. And a lot of it trends towards microservices where things are hosted randomly all over the globe. And that threat model and that attack surface needs to be analyzed and understood by the end consumers and implementers of this software. And we need, as a group like OpenSSF, we need to concentrate our resources on critical libraries, critical components, and projects to help provide the most bang for the buck. There are a lot of different tools available, and we'll talk a little bit about some of the things the Foundation's doing about that. But static analysis, fuzzing, peer code review, these kind of traditional software engineering practices need to be more fully adopted within the community. And we need to perform kind of enhanced testing. And that's where that manual code review, and we have a project we're partnering with an organization called OSTIF, where we're going to go through and do code reviews of specific high critical projects. And then, kind of thinking forward, we need to participate more in things like coordinated vulnerability disclosure. The open source ecosystem is broad and diverse, but we can provide some simple rules, some simple guidelines and templates that people can refer to and use, and help educate the value of coordinated vulnerability disclosure to reduce the end risk for those end consumers. And things like software bill of materials helps describe what's inside that piece of software you're just downloading, that container you're using, that that pull request you just made, kind of what's in there. And there's also improvements we're making with the larger CVE community to help improve the speed and ease of use of getting these vulnerabilities identified and communicated out. But at the end of the day, the TLDR of it is, what actually helps open source be more secure? I'm going to give you a groundbreaking idea. Give you a minute. I'm going to blow your mind. If you use software from a project, maybe on some level you can contribute back to that project to help them improve the quality of their software, help them improve the speed of their delivery, the quality of their overall product. I know, I just blew your mind. It's an amazing novel concept. So kind of what we can do, I touched on it very briefly. Threat modeling, understanding where and how a project can be compromised, both at a software level, the engineering perspective, this is how this coding mistake is, why that's there and how to eliminate it, but also thinking about how that project works. Where's their repository? What's their CI/CD pipeline look like? Think about how that can be compromised by a bad actor. We need to help work to identify the most critical open source projects and invest time and resources to help them do better, to help improve the overall ecosystem for everybody. And again, things like preventing vulnerabilities in the first place, using tools like Dependabot to help as you're checking in code or downloading code, you're able to see kind of what the dependencies are, or doing automated vulnerability scanning before even using something, and implementing SDLC-like practices across the board, whether for big projects and small projects. It all kind of boils down to there's a lot of potential inherited security debt here. When you are using software that you didn't write yourself from unknown sources, that there's an aspect of risk that you need to think through and understand how can you help protect yourself? How can you help protect that project? Tools like the CII Best Practices badge help give you a list. These are projects that have been vetted and meet expected criteria on varying levels. There are investments that can be made in tooling to help bug hunting, scale up more and help remediation happen more. It's great to find a lot of problems. Your boggle is you have more people finding problems than you have people fixing the problems. So how can we help fix the problems? We need to invest in things like security reviews. We need to have coordinated patching and incident response. If one project fixed something somewhere and there are other related projects that don't get the fix, that's still a failing. There's a gap there in that model. We need to figure out how we can help make sure everyone gets aware that there's a vulnerability and there's something that needs done, and those that can contribute have that ability. We need to have that more thorough, more consistent vulnerability disclosure process. When a user of open source software is using a project, they need to understand how that project works, how they handle vulnerability intake, how they fix stuff, who else they might include. And again, I think where we can have coordinated and impact prioritized funding for these improvements, audits, and further research in how we can help the model going forward. Thinking back, this is not the first time in history people have invented, come together to help solve the open source problem. Thinking back to the dawn of time, back in 1988, we had the Morris software worm that kind of got people to realize, hey, there's a problem on the internet and all these things are connected and bad stuff could happen. In the early 90s, Linux was created. Yay! Around the year 2000, there was a little problem called Y2K that the whole world was going to end in December 31st, 1999. Spoiler, it didn't. But that was, again, there's another area where people realized there was a problem with computer software. They got together and helped try to fix it. Our friends over at OWASP got together in 2001 and started initially focusing on web application security, but over the years they've branched out to be broader, just application security. Remember, I mentioned back in 2014 we had Heartbleed that kind of woke a lot of open source people up, and later that month there was a project created called the Core Infrastructure Initiative that started to fund people and resources and tooling to help assist projects like OpenSSL. But then again, we were reinforced, kind of the ubiquity of open source in that September when we had Shellshock, which was a bash vulnerability. Our friends over at OWASP created a great kind of a testing tool, ZAP 2015. Folks over at Google started a project called OSS Fuzz in 2016. We have Dependabot that came out in 2017. The Open Source Security Foundation came together in 2020, and we're partnering with organizations like OSTIF and others to help improve the overall quality of open source ecosystem. And who knows where we're going to go in the future when we're all wearing silver spacesuits and flying around in our cars. It's going to be awesome. So, how can we help? You can help today by participating. There's great ways. There's many different groups that you can join in. You can contribute your knowledge by writing software, by providing comments, helping with documentation. You have to remember, we're all in this together. It's an ecosystem. Sharing is caring. We all use the software. Let's all try to find ways we can help to improve it. Now, thinking about how the OpenSSF specifically is working on this problem, we have 6 different working groups today. We have identifying security threats, securing critical projects, digital identity attestation, security tooling, my favorite working group, the Developer Best Practices working group, and then my favorite working group, the Vulnerability Disclosures working group. And we have a lot of different projects we're working on. And these are tangible items that people could participate in, active development that's going on. So, for example, we have projects like the metrics or the badges or things like SKF or CRE that or OSS Fuzz that the foundation is working on. We have members working on. We do some academic stuff, like where we have a listing of personas and persona pain points. We have white papers. We also work with industry groups. There are several things that are affiliated, things like in the developer identity space, like you have Keylime and Toto and SigStore that aren't part of the foundation but are affiliated, and they're working towards enhancing pedigree and provenance of open source software, so people that use open source software have assurance that it's coming from the right place and wasn't changed. And then we are working towards creating best practices for the ecosystem on here's tooling that is great options for an open source project to use. If you use these languages, here's secure coding guides we can help you refer to so that you can write better quality software. And that whole all-important CVD. Here's what CVD is, here's how you can do it, and how you can participate, resources that are available to you to get vulnerabilities documented. And if you need help doing it, we can help provide you resources to help find out how to do that. And then thinking about the larger ecosystem, we partner with organizations like CertCC. There's a vulnerability reporting platform called Vince. We're working with them onto open source. And then they'll think about the larger efforts like the NTIA's SBOM, Software Bill of Materials effort. The foundation is involved in a lot of these different things. And there's always room for improvement, but there's also always room for your participation, your feedback, and your collaboration. And I'm going to pass it over to Jennifer to take us home here.
We currently have 6 working groups that are working on things like building scalable tooling for open source software in general, including the development of scorecards to help users better understand the security properties of a given repo or package, improving coordinated disclosure for open source software, developing security guidelines for open source developers, combined with tooling like the CII Best Practices badge to encourage projects to reach a certain minimum level of security standard, and perhaps most interestingly, our Securing Critical Projects group, which seeks to define the most critical projects on the internet for the targeted investment of time and other resources for things like research, development of tooling, partial rewrites of code in safer programming languages, and third-party security audits. Thank you for listening. Please join us by visiting openssf.org/getinvolved, and we will now share further details about our work and take any questions.